All right, video 2 here for lesson 6.2 on exponential functions. Let's do a couple application questions. All right, so example 2 says graph exponential functions. It says a network administrator uses the function f of x equals 5 to the x to model the number of computers a virus can spread, or computers a virus spreads to after x hours. If there are 1,000 computers on the network, about how many hours will it take for the virus to spread to the entire network? So here is our function, right? F of x equals 5 to the x. So in this word problem, x is hours. So that means y is computers. So your y variable is the number of computers. So the idea here is that we have this function, and we want to know when, at what time, will our y equal 1,000, right? So this is our y value, 1,000. So we're going to graph this on Desmos. Because they don't give us an x to plug in, they give us a y value. We need to use Desmos graph and kind of estimate where this is going to be. Okay, so you have this graph here. I'm going to show you on Desmos what the graph will look like, and then we'll try to do a rough sketch on here. Okay. All right. So let me get Desmos open here, right there. All right. So the first thing I'll do is I will type in f of x equals 5 to the x. Okay, and there's your graph. Now, one thing I want to show you is if you click this gear, okay, and you click on that table symbol, it will show you a table of values, right? So notice here, right? So a couple things. Notice first this point 0, 1. So if we take this as y equals a times b to the x, right, or f of x equals a b to the x. Your b value is 5. This is the number by which we're going to multiply the y values to get the next y value. And this a value is your initial amount. Well, there's no number here. So the a value is a 1, and that's why your y-intercept right here is a 1. Now let me zoom out 1. You know I like to do that, right? So if I hover here, that's my y-intercept, 0, 1. That's my starting point. So notice here, again, if you multiply by 5, you get 5. Multiply by 5, you get 5. So that's how these are growing, right? By a factor of 5. Okay. You can, in this table, if you click enter, you can enter more values. So what if x is 3? After 3 hours. What about after 4 hours? What about after 5 hours? Notice here, right? Notice here, y is the computers. Notice we go from 625 to 3125. Your value of 1,000 is somewhere in there. Right? So if we can get a good picture of this, we can kind of estimate where our time frame is for the whole network to be covered. All right, so what I'm going to do is I want to plot these on our graph. Okay, so I'm going to take this right here, these numbers, and put them on our graph. Okay, so let's go back to our other problem. Okay, so here's our graph here. So on here, this is our x. So here's 0. We're going to count by ones down here. So 1, 2, 3, 4, 5. But up here, right, I want 1,000 to be on here. Right, so if we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If we count by 100, so 100, 200, 300, 400, 500, 6, 7, 8, 9, 1,000, all the way up to 1,200. Right, we'll be able to graph a lot of the values there. So in that XY table that we got from Desmos, right, so 0, 1, that's the initial point. Going to be way down here, right, 0, 1, 1, 5. Going to be here just a little bit higher, still really low. 2, 25, right? These are just like 5 to the second power, right? 2, 525. So 225. Now 25 still less than 50, so it's not even quite half of that box, right? 3, and now this is 125, right? 5 to the third is 125. So now we're going to go up here above 100, just a smidge. And then 4, 625. Again, I'm just remembering this table from Desmos, right? So 4, here's 500, 600 a little bit. And then remember, 5 was where it jumped to that 3125. So that's way up here. So if I go ahead and connect those, right? Make sure you use that sound effect when you do that. And again, if you think about connecting that way up there, This is your exponential graph. That's what 5 to the x looks like, this thing. Okay. And now, if I take another color, and this is y equals 1,000. If I go to where y is 1,000, right here, and I draw a horizontal dotted line across, this point right there is an x value, and the y is 1,000. Notice it's somewhere between 4 and 5. So I'm going to go back to Desmos, type in y equals 1,000, and get a better picture. But this is the graph we want to see in your notes. Okay? All right, so let me clear that. Let me go back to Desmos here. Okay, so I'm going to zoom out so that I can see. Let me change the scale real fast. Here you go. So go back to here. Let's click the wrench. Our x-axis, let's go from 0 to 10. Our y-axis, let's go from 0 to 1,200, like I had on our graph. Okay, so make sure you have those numbers correct there. And now, let's type in the next box down here, y equals 1,000. And there you go. There's that point, and look what we want. 4.292 1,000. We're going to round that to the nearest one decimal. That's 4.3. So that intersection point, go ahead and put this on your notes, is 4.31 thousand. That means that it took 4.3 hours for the virus to infect the entire network. Now, we can check this, right? This is just an estimate. We can check this by plugging this in for x. So if we do y equals 5 raised to the 4.3 power, we can check this in Desmos to see what it comes out to be. It should be really close to 1,000. So let me come down here. I'm not going to type in the y equals, just type in 5. Again, use the caret button, which is shift 6, and I'll do 4.3. And notice because we rounded up, it's going to be a little bit more than 1,000. So we got 1,000, I'm going to go 13, and that'd be computers. So in 4.3 hours, this virus would affect 1,013 computers. All right, very good. Okay, next question. Okay, what is the written form of the function represented by this table? So this is a very important type of question, right? The state test loves these type of questions where they give you a table of values. So remember, this is the formula we're going to fill out. F of x equals a b to the x. Okay, remember, this a is your initial value, which is your y-intercept, and this b is your ratio, right? How your y's are changing. Okay, so notice this first row right here. When x is 0, y is 4. This is your y-intercept, 4. So that's going to be your a value. All right, so down here, I already know this is f of x equals 4. And now I need the ratio. So now what you have to do is you have to go, and I'll use blue, you have to go in that y column. What do you multiply 4 by to get 12? Or 12 divided by 4 gives you what? Because if you know that, that'll be that common ratio. And 12 divided by 4 is 3. So now do the next one. 36 divided by 12. That's also 3. Do the next one. 108 divided by 36. This can be done in Desmos. That's also 3. And do the last one. 324 divided by 108. That is also 3. Because each of these quotients, right, answer to division problem, comes out to be 3. There is your ratio, 3. And that is your b value, right? So this is your ratio. Let me spell out the word ratio. So your ratio equals 3. So that goes here to the x. So this is what your function will be. Remember, you can also have it without the parentheses, 4 times 3. That's a times symbol, times 3 to the x, right? Either way you slice it, it'll work. Okay, next. So now this is a table of values. Now let's do a graph, right? Same thing. What is the written form? So again, I want f of x equals a parentheses b to the x. Okay? So again, I want that initial value, right? So what is that y-intercept? Well, if you look here, here's the y-intercept. That's going to be your a value in this problem. So f of x equals 128. parentheses, and now I'll change colors. So now we're looking at the y values. What do I do to get from 64 to 128? Well, if you take 64 and divide it by 128, divide it, you're going to get 0.5. Do the same thing. Take 32 and divide it by 64. You're going to get 0.5. Take, oh, now be careful here. Watch. I did not see this 316 here, right? You cannot go from 232 to 48 because they're not consecutive. All right, so hopefully that makes sense. So be careful there. So now I'm going to go here from 32 to 16. 32 divided by 16 is, 16 divided by 32. Second divided by the first. 16 divided by 32 is 0.5. And now we go from 16 to 8. 8 divided by 16 is 0.5. And then we go from 8 to 4. 4 divided by 8 is 0.5. So notice, each time you step down this graph, the y values are being multiplied by a half. That's your ratio. So your ratio is 0.5. You could also use a 1/2 if you want to. It doesn't matter to me. So that would be 0.5 to the x. Okay, that wasn't even better. You could also do again without the parentheses, 128. I'll use the 1/2 this time, times 1/2 to the x. Probably with the 1/2 you want to use parentheses, right, just because it's a fraction. Okay, so either way is going to work. All right, last but not least, number 4. Compare a linear to an exponential. This is an important idea. The state test loves this. Talicia's offer 2 pledge options for donating to a charity. Which option will increase faster over time? Which will increase faster over time? So we have option A. We're going to give $100 for the first week, and then each week after that, we're going to increase by 25. Option B, $1 for the first week, and then each week after that, the amount triples. So if you look here initially, you might say, well, if you're going to start with 100 here and only $1 here, of course the 100 is going to, end up giving more money. Okay, but again, you have to be aware of this idea of increasing by 25 versus tripling. Okay, option A is a linear option. So in this option here, right? F of x equals, you're going to start with $100, and then you're going to add $25 for each week, so plus 25x. So x is the number of weeks here. So x equals number of weeks. Okay. So let's do the first couple, right? So let's have a week. So your x and your f of x, right? So this would be the week, and this would be the amount. So first, so we let 0 be the initial amount, right? And that's $100. So after another week, so once 1 week passes, you're going to add 25 to that. That's 125. After 2 weeks, that's another $25, 150. 3 weeks, 175. 4 weeks, 200. Let me move this up here. 5 weeks, 250. 6 weeks, 5 weeks, 225. Sorry about that. 5 weeks, 225. And 6 weeks, 250. Right, let's stop there for the meantime. Now let's come over here in blue, and let's do the exponential. So this is an exponential because you're tripling each time. So now, we'll call this g of x. Your initial amount is $1, and then you're tripling each week. Right, so there's your function, right? So here's x, here's g of x. So again, the 0th week, the initial week, you have $1. After the first week, this triples to 3. After the second week, that triples to 9. We're just times it by 3. After the third week, that triples to 27. After the fourth week, so notice you're still pretty relatively low compared, right? After the fourth week, this triples to 81. After the fifth week, this triples to 243. And now watch. Look at that. Look. Boom. We have now jumped. The exponential model is now at a higher amount than the linear model. So now when you go to the 6th week and I times this by 3 again, that's 729. Look at how much bigger 729 is compared to 250. So which option will increase the budget amount faster? It's the exponential, option B. So our answer here is option B. Option B, hold on, sorry. Option B, which was the exponential option, increases faster. And I'm going to put in parentheses week 5, because week 5 is when the exponential takes over from the linear. Again, our state test loves the idea of how exponentials grow faster than linear. Okay, so keep that in mind as you go forward from here. All right, thanks for watching. We'll see you in class.